In this video, we're going to talk about exponential functions. So suppose that we have a constant b, so a real number b, which is positive and not equal to 1. Then what we are going to do is we will define a function f of x equals b to the x. So for example, we will define f of x equals 2 to the x, or 3 to the x, or just any positive number like 1/5 to the x power. And we'll see that this function is useful for describing what's called exponential growth or exponential decay. But before we can do that, we have to make sense of what b to the x even is. So we will define what b to the x is for any real number x. And to do that, we have to proceed in several steps. So the first step is to define it when x is a positive integer. Well, that's easy. We'll define b to the x to be what you get when you take x b's and multiply them. So for example, if b is 2 and x is 5, then 2 to the 5th power is defined to be 2 times 2 times 2 times 2 times 2, which is 32. So this is something that you are already familiar with. So that is what you do for b to the x when x is any positive integer. Now what if x is 0? Then we define b to the 0 to be 1. Okay, why do we define, so this is a definition, we define b to the 0 power to be 1. Well, so why do we define it like this? Because when we define b to the x for a positive integer, we have two properties. One property is that when you have b to the m raised to the n, this is b to the mn power. And the second property is that when you have b to the m times b to the n, this is b to the m plus n power. And it turns out that these properties, well, they make sense for step 1 when m and n are positive integers. But we're trying to define b to the x in a way that this is true no matter what m and n are. So m and n can be any real numbers, and then the property would be true. So the question we ask is, what would you have to define b to the 0 in order for the properties to hold when m and n could be 0? Well, if we want property 1 to hold when m is possibly 0, we would need that if you take b to the 0 plus 1, okay, that's the same as b to the 0 times b to the 1, right? If you take m to be 0 and n equals 1, then you would get b to the 0 times b to the 1 equals b to the 0 plus 1 power. Well, that would be b to the 0 times b to the 1 is b equals, and then on the right, you have the power, which is 0 plus 1. 0 plus 1 is 1, so you have b to the 1, which is b. And now you divide both sides by b, you get b to the 0 equals 1. So if you want the properties 1 and 2 to hold for all real numbers m and n, then you are forced to define b to the 0 to be 1 because you need this to hold. So you want it to be the case that b to the 0 times b to the 1 is equal to b to the power 0 plus 1. And if that were the case, then that would imply that b to the 0 is 1. And so that's why we define b to the 0 power to be 1, in order to have this nice property. Okay, so that's when x is 0. Now the next step is to define it when x is a negative integer. So let's say that you have b to the negative n, where n is some positive integer. Right? Then negative n is a negative integer. So the question is, how should we define b to the minus n? It doesn't make sense to have, negative n b's and multiply them, right? That doesn't make any sense, obviously. And just like it doesn't make any sense to have 0 b's and then multiply 0 b's together and somehow get 1. That also doesn't make any sense. So when we're kind of extrapolating to x being not necessarily a positive integer, this interpretation of taking a certain number of b's and multiplying it, that doesn't apply. What we're using instead are these properties, 1 and 2, that I listed, that we want to have happen, and we're trying to think about what would b to the minus n have to be in order for these properties to be true. Well, we know that b to the 0 power is defined to be 1. So if you have b to the n, let's think about what b to the minus n would have to be if b to the minus n times b to the n were equal to b to the minus n plus n. Well, negative n plus n is 0, b to the 0 power is 1. So we want b to the minus n times b to the n to be 1. So then if you divide both sides by b to the n, you see that you're forced to define b to the minus n to be 1 divided by b to the n. So we define b to the minus n to be 1 over b to the n. So for example, okay, let's do an example for number 2 here. So 2 to the 0 power is 1. Okay? So for an example for 3, if you have 2 to the minus 3rd power, this would be defined to be 1 divided by 2 cubed, which is 1/8. So that's now the definition of b to the x whenever x is any integer. We've defined it for positive integers. You just take, if x is a positive integer, you just take x b's and multiply them. If x is 0, you define b to the 0 to be 1. And if x is a negative integer, then it's just 1 divided by b to the absolute value of that integer. Right? You just make it positive and then 1 divided by b to the number. Okay, so that's when x is an integer. Now we have to go on to the next step, which is when x is a fraction that's not necessarily an integer. So if you have something like 1 over n, where n is a non-zero integer. So for instance, what would be 2 to the 1/2 or 2 to the 3rd, or how do we make sense of that? Well, again, it doesn't make sense to take half of a 2 and multiply it together. What we're doing is we're, again, looking at properties 1 and 2 and thinking about what would 2 to the 1/2 or 2 to the 1/5 have to be in order for properties 1 and 2 to work for all real numbers m and n. Well, if you look at property 1, Okay. What we want is we want b to the 1 over n raised to the nth power to be b to the 1 over n times n. This is when you take m to be 1 over n. Right? So we want the left-hand side to be equal to the right-hand side so that we have this nice property. And 1 over n times n, the exponent, is just 1. So this is b to the 1, which is b. So we see that we want b to the 1 over n to be such that the nth power is b. Well, now you take the nth root of both sides. Of both sides, b to the 1 over n to the nth power equals b. And you see that in order for those to be equal, you need that b to the 1 over n has to be equal to the nth root of b. So that is the definition of b to the 1 over n. It's the nth root of b. Which, I'll just remind you, has to be a non-negative number. Okay? So we define it to be, the non-negative nth root. So for instance, 2 to the 1/2 power means the square root of 2. 2 to the 1/5 power means the 5th root of 2. This is actually when n is positive. Okay, so 1 over n is positive, but you can also have negative. So if you have like b to the negative 1 over n, where n is positive, so b to the negative fraction, you want this to be b to the 1 over n to the negative 1 power, because 1 over n times negative 1 is negative 1 over n. Right? So we want the left-hand side to be equal to the right-hand side. And that is the case. Well, if that is the case, then what would have to happen? The right-hand side is something to the negative 1 power. And so we would want it to be 1 divided by b to the 1 over n. So for instance, 2 to the negative 1/3 power would mean 1 divided by 2 to the 1/3 power, which is also 1 divided by the cube root of 2. So that's how you define b to the x when x is 1 over n. Now we just need to figure out what to do when x is, say, m over n, where m and n are just any integers. As long as n is not 0, right? Well, again, we want this property of b to the m over n raised to the nth power. Okay, maybe I'll write it like this. We want b to the 1 over n to the nth power to be b to the m over n. So that way you have this nice property, right? This exponential property. So, well, that's how we define it then. We define b to the m over n to be b to the 1 over n raised to the mth power. So for example, 2 to the 5/3 power is defined to be 2 to the 1/3 power raised to the 5th power. So that's the cube root of 2 raised to the 5th power, which you can write as, so this is the cube root of 2 cubed times the cube root of 2 squared. So this would be 2 times the cube root of 4. Because how did I do that? Because if I have the cube root of 2 times the cube root of 2, I have this property that it's like this, and then that's the cube root of 4. So now we've defined a constant raised to a fraction power, a fraction exponent. Then the last step, is what happens when you have a real number that's not a fraction? Like the square root of 2 or pi. Like what would be 2 to the pi power, 2 to the square root of 2 power? What is that? So the way you do it is you remember that when you have an irrational number, it has an infinite decimal expansion. So for instance, pi is 3.1415, and it just goes on forever. The square root of 2 is 1.414, ... it goes on forever. So the way we define it, I'm just going to write out the examples for pi and the square root of 2 instead of just writing out like a general formula. The way we define something like 2 to the pi, or b to the pi, is we make a table. So to define b to the pi, what we look at is the list, or you could put this in a table, b to the third power, then b to the 3.1 power. So remember, when you have a decimal that's terminating, so, right, that just stops, it corresponds to a fraction. So 3.1 is 3 plus 1 over 10. So that's 31 tenths. And if I have 3.14, that's 314 over 100, right? So we've defined b to the 3, b to the 3.1, b to the 3.14, and so on. So what we do is you look at b cubed, b to the 3.1, b to the 3.14, b to the 3.141, and you keep going, b to the 3.1415, ... and then you look at what number the numbers in the list are approaching. So for instance, if you look at 2 to the pi, okay, to define 2 to the pi, you look at 2 to the 3.1415, and then 2 to the 3.14151, and that's going to give you some number. And you just keep looking at what number these numbers are approaching. So these numbers approach a number, and we call it 2 to the pi. So for instance, if you look at a graphing calculator or something and plug in 2 to the pi power, you're going to get this infinite decimal. And if you do 2 to the 3.14151, it's pretty close. And then if you do 2 to the 3.1415, oh, that's 159, 1592, right? Then you get even closer. And as your exponent gets closer and closer to pi, your outputs, your values get closer and closer to 2 to the pi. So that's how you define 2 to the pi. It's that number that the numbers are getting closer to. And similarly for 2 to the square root of 2, okay, so for 2 to the square root of 2, what you do is you look at 2 to the 1.414, and then 2 to the 1.414, let's see, 2 to the 1.41421, and you look at what these numbers are approaching. So they approach a number, and we call that number 2 to the square root of 2. So that defines 2 to the power of any irrational number. And since any real number is either rational or irrational, we know that this defines 2 to the x for any x, or b to the x for any real number x. So let's review the process one more time. So step 1 was to define it when the exponent is a positive integer. Step 2 was to define it when the exponent is 0. Step 3 is to define it when x is a negative integer. So that takes care of all integers. Then, step 4 is to define it when the exponent is 1 over an integer. So 1/5, 1/6, negative 1/7, etc. Okay, we define it when you have a positive exponent, it's just defined to be the nth root and of b, and when you have a negative exponent, it's 1 divided by b to the 1 over the absolute value. So b to the negative 1/7 is defined to be 1 divided by b to the 1/7. Okay, which is, just to be clear, is 1 divided by the nth root of b. So that's when your fraction is 1 over n. Then once you have that, it's an easy step to go to m over n. That's just b to the 1 over n raised to the power of m. Okay? And then the last step is when you have an irrational number. And when you have an irrational number, it can be approximated by this infinite list of fractions of rational numbers. So pi is what you get when you start off with 3, then 3.1, then 3.14, and you keep going and you get closer and closer to pi. And when you do 2 to that, so 2 to the 3, 2 to the 3.1, 2 to the 3.14, etc., those numbers are approaching a certain number, and that number is what you call 2 to the pi. And in general, you can do that for any irrational number at any base. And so that defines b to the x for any real number x. So that is the exponential function f of x equals b to the x. So this is how we define b to the x. The function f of x equals b to the x. Right? Because to define a function, I have to tell you what it does to every single input. Well, I'm trying to define it so that the input is any possible real number. So I have to tell you what it means to do b to any real number. And that's what we talked about in this video. So it turns out that when you define b to the x this way, the function f of x has some nice properties. They're just the properties that we talked about before. It's that b to the m plus n is equal to b to the m times b to the n, and b to the m raised to the n power is b to the power of m times n, but this time it's for all real numbers m and n. So for instance, if you had b to the pi power raised to the square root of 3 power, this will be equal to b to the power of pi times the square root of 3. Or if you had b to the 1/7 power raised to the negative 50th power, this will be equal to b to the negative 50 over 7. So those are some properties of these functions which we call exponential functions. So these functions are called exponential functions. And we'll talk more about properties of these functions and how they're used in a later video.